In the last class, we have seen double sideband suppressed carrier. In the previous class, we have seen double sideband full carrier. What is the difference between double sideband full carrier and double sideband suppressed carrier? I mean, the difference is in the power distribution. So, for transmitting the carrier alone, we are wasting 2/3 of the power. By suppressing the carrier, we are saving the power, the transmission power. But suppressing the carrier alone will not increase the transmission bandwidth. Therefore, we are going for another one modulation technique in the amplitude modulation. This one we are naming it as single sideband suppressed carrier. Previously, we have achieved decrease in the transmission power. So, in short, we name it as SSB-SC. So, in DSB-FC, we have seen, and DSB-SC, we have already seen the full carrier and suppressed carrier. The transmission bandwidth is equal to twice the modulating frequency, and the transmission power is transmission power efficiency. We have calculated it as transmission efficiency for DSB-FC. We have calculated it as 33.33%, and for we achieved increase in transmission power in double sideband suppressed carrier, that is amount of useful power 66.66%. Here in single sideband suppressed carrier, we are achieving the reduction in transmission power, How we are achieving the reduction in transmission power? By suppressing the carrier. And we are achieving reduction in transmission bandwidth. How we are achieving that reduction in bandwidth? By suppressing one of the sideband. Since only one of the sideband is sufficient to effectively recover the message information, we can suppress any one of the sideband. Either we can suppress lower sideband or we can suppress the upper sideband. By using either the lower sideband and upper sideband, we can effectively recover our message signal. Therefore, this type of modulation, when we suppress our carrier and suppress our modulation, this type of modulation is referred as SSB-SC. The time domain representation for SSB-SC is given by time domain representation. In the graphical representation also we are going to see time domain representation and graphical representation. Here we are going to achieve single sideband suppressed carrier by using the double sideband suppressed carrier waveform. Therefore, we know the output waveform for the double sideband suppressed carrier. This is our message signal. When we combine our message signal with the carrier, this is our minus Fc and this is our plus Fc, and this is our carrier signal in frequency domain representation. So, our double sideband suppressed carrier waveform is given by our carrier will be suppressed here. So, this is minus Fc and this term is plus Fc. This term is presented as double sideband suppressed carrier. So, when we pass this double sideband suppressed carrier waveform into a sideband filter having a characteristics of, please ignore this, having a characteristics of minus Fc and Fc and F. This is our sideband filters transfer function. How we can get this transfer function? By combining the signum function. So, this is our signum function, signum of F minus Fc. So, this is our minus Fc, this is our on. Amplitude will always be plus or minus 1. And the second spectrum we are combining with this is, this is a 0, this is Fc. So, this is minus signum of F minus Fc. So, by combining these two waveforms, we are getting the transfer function for our sideband filter. So this is our sideband filter. So when our double sideband suppressed carrier waveform is passing through the sideband filter, we are getting the single sideband suppressed waveform. Here we have used the lower sideband filter, therefore we are getting only the lower sideband. If the bandwidth is chosen according to that of the upper sideband, then we will get only the upper sideband portion. So this is our Fc, this is Fc minus of W, 0, this is our minus Fc, this is minus Fc minus W. This is our single sideband lower sideband filter. This is the graphical representation. Now we are going to see the first waveform. This is our message signal, this is our carrier signal. By combining the message signal and carrier signal using the product modulator, we are getting the double sideband suppressed carrier waveform, and by passing this double sideband suppressed carrier waveform, this is fourth one, via a sideband filter, we are getting the single sideband filter having only the lower sideband. This is, we are representing it as LSB, lower sideband. So we are getting only the lower sideband. We have suppressed the carrier part. This carrier is suppressed here, and we are getting only the lower sideband portion. Either it will give the upper sideband or lower sideband filter. We can draw a block diagram for the easy understanding. So what we have mentioned, we have to apply our message signal and carrier signal to a product modulator. Carrier signal, we know that AC cos omega CT, and the resultant will be our spectrum of double sideband suppressed carrier, and when passing this to the sideband filter, here the ideal filter, we have chosen the passband as to filter out only the lower sideband. If it is for upper sideband, we have to use HU of F, the transfer function, and according to that we will get either lower sideband waveform or upper sideband waveform. So this is our general block diagram. The transfer function is given by, for our assumption, we will take only the lower sideband filter. Understand the derivation part. So therefore the transfer function of is given by HL of F is equal to 1 by, we have seen here, 1 by 2 into signum of F plus Fc minus of signum function F minus of Fc. We will take this as equation number 1. We know that SLSB, output of the single sideband filter, is given by SLS of F is equal to S spectrum of double sideband filter together with the transfer function. So we are taking this as equation number 2. This is the output of sideband filter. We know that our double sideband suppressed carrier is nothing but the multiplication of product output of the product modulator. So M of t into C of t. M of t is nothing but M of t, we know that AM into cos omega mt. C of t is AC cos omega CT. We are taking this as equation number 3. Here we have taken a time domain representation. In these two, in the first two equations, we have taken the frequency domain equations. Therefore, we have to convert our equation number 3 into one frequency domain form. How to convert our time domain equation into frequency domain form? We have to take the Fourier transform. Therefore, for Fourier transform representation of equation number 3 is given by AC by 2. We know the M of t into cos omega CT is replaced by M of F minus Fc plus M of F plus Fc by using the Fourier transform pass. This, instead of this equation, we are taking this as equation number 3 because all 1, 2 and 3 are in frequency domain representation form. Therefore, we have to substitute this equation number 3 in equation number 2. After substituting equation number 3 in 2, spectrum of single sideband suppressed carrier is given by AC by 2 m of f minus fc plus m of f plus fc plus, sorry, here is a multiplication, since here transfer function is multiplied with the spectrum of double sideband suppressed carrier. Therefore, here we are going to substitute equation number 1 also in equation number 3. Substitute equation number 3 into 3, 1 and 2. Therefore, signum of f plus fc minus of signum of f minus fc. So, by taking the cross multiplication, AC by 4 m of f minus fc signum of f plus fc plus AC by 4 m of f minus fc f plus fc signum of, here we will write it here, signum of f plus fc, and then minus m of f minus fc signum of f minus fc minus of m of f plus fc and then signum of f minus fc. We have got 4 terms, one with minus and plus combination, that is alternate combination, and another 2 terms with same same number of negative negative and positive positive, same kind of operators. Here it is opposite type of operators. So, by using this equation, we are going to find out one observation. We know when any of the signal is combined with the signum function, when any of the signal is combined with the impulse function, that the same signal will be reflected in the output part. So, the same thing is applicable for signum function as well. Therefore, we are making the following observation: product of any number with 1 will yields 1, the product of the number. Therefore, x multiplied with 1, we are end up with x. Therefore, m of f minus fc signum of f plus fc will be the resultant will be m of f minus fc. We have taken only the opposite part. Therefore, similarly m of f plus fc and signum of opposite operators m of f plus fc and then signum of f minus of fc, again the resultant will be minus of m of f plus fc. So, we are going to substitute these 2 observations in the equation. Here we are going to end up with S of L SB of f is equal to AC by 4 m of f minus fc plus m of f plus fc minus of AC by 4. This we will take it as a single term, and the remaining term which we were not able to sort out, which we are going to sort out by using another one interesting transform, signum of f minus fc minus of m of f plus fc into signum of f plus fc. So, now we are going to see an interesting transform called Hilbert transform. We have seen Fourier transform. Fourier transform will convert time domain into frequency domain and vice versa. In this Hilbert transform, H of t transform, Hilbert will not transfer from one domain to another domain, that is from a time domain to frequency domain. It cannot be transformed. It changes only the time domain signal. The purpose of Hilbert transform is to change the time domain signal into another time domain signal. How to convert the time domain into another time domain? Does it make any difference? It phase shifts all the frequency component. What Hilbert transform will do is, it will phase shift all the frequency components in one time domain or from the input signal. Phase shift all frequency component in the input signal or in the by minus pi by 2 radians. Therefore, we will get only the phase shift. There is no transformation in the domain, that is, it cannot be transferred from time domain to frequency domain. It will maintain the same domain from time domain to time domain, but only the phase shift alone will get changed. For example, imagine we have a signum function. We know the signum function is given by 1 when f is greater than 0, 0 when f is equal to 0, minus 1 when f is less than 0. Therefore, the signum function is given by 0, this is minus 1, this is plus 1, this is our signum function, signum of f. The magnitude will always be 1 for all frequencies and the angle of h of f is minus pi by 2 for f greater than 0 and pi by 2 for f less than 0. The Fourier transform of Hilbert transform is given by j divided by pi by t. Fourier transform always gives signum function. This is the important transform which we are going to use this result in our single sideband suppressed carrier. With the help of Hilbert transform, we know that m of t when convolving with the h of t, the Hilbert transform filter will get m cap of t. In terms of frequency domain, m cap of f is equal to m of f. Convolution in time domain will result in multiplication in frequency domain, therefore m of f into h of f. We have seen the transform of Hilbert transform. The Fourier transform for the Hilbert function is given by minus j by pi by t. We can replace it as minus j into signum of f. Therefore, minus j signum of f into m of f after substituting the Hilbert transform. So, we are going to use this result for this equation. If we substitute f instead of f plus fc, the above equation, consider this as equation number 5. This equation will becomes m cap of f plus fc minus j of signum of f plus fc m of f plus fc. Similarly, when you substitute f minus fc, our equation number 5 will becomes f minus of fc minus j of signum of f minus fc m of f minus fc. Therefore, we will substitute these two results in equation number 4. LSB of f will become AC by 4 m of f minus fc. The first two terms we are taking as such, and this remaining two terms will be replaced by minus AC by 4 minus 1 by j m cap of f minus fc plus 1 by j m cap of f plus fc. So, we know that the Fourier transform for the cosine function, cos function and the message function, that is 1 by 2 into AC m of t cos 2 pi fct will become AC by 4 m of f minus fc plus m of f plus fc, and m cap of t for the sine function e power plus or minus e power that is 2 pi fct, imaginary part j, will give m cap of f minus and plus fc. This is for our sine function and this is for our cosine function. Therefore, our equation, we will take this as equation number 7. Our equation number 7 will become as LSB of f is equal to 1 by 2 into AC m of t cos 2 pi fct plus this term will be replaced as cosine form into m of t, and this term will be replaced by ac by 2 m cap of t sin 2 pi fct. This is for our lower sideband filter in single sideband suppressed carrier. If it is for our upper sideband S USB, then our term will be 1 by 2 AC by 2 m of t cos 2 pi fct minus of AC by 2 m cap of t sin 2 pi fct. So this is the time domain expression for our single sideband suppressed carrier. We have already seen the spectrum for lower sideband. If this is our, we'll draw here for the upper sideband. So this FC plus W. This is a frequency domain, but F is of upper sideband. So minus FC minus W for upper sideband. 0 center frequency. Now we are going to see the generation and demodulation, generation and detection of single sideband suppressed carrier. So far we have seen the time domain representation and graphical representation of single sideband wave. Now we are going to see the generation and detection of single sideband wave. First we will see the generation. What are all the methods available in the generation of single sideband wave? Here we are going to see two methods. First is filtering method, or it can also be mentioned as phase frequency discrimination method. The second one is phase shift method. First one is filtering or frequency discriminator method. Second one is phasing or phase shift, or it can also be mentioned as Hartley method. First we will see the filtering method. The practical difficulty which we are facing in the sideband filter is either the portion of the, we have seen the single sideband filter which is having minus FC to plus FC. So it have to abruptly cut off the, see here this is our double sideband suppressed carrier waveform in the frequency domain. So this is our HL of F and this is our SDSB SC waveform in FC in 0 1, this is our F. So our sideband filter have to cut off exactly in this center frequency of the carrier signal, but the practical filters or physically realizable filter cannot be used to achieve this desired waveform, because practical filters will either pass the desired undesired waveform or it will attenuate the desired waveform. That is, it will either pass undesired portion, because sharp transition is not possible in the physical realizable filters. It may pass undesired portion or it will attenuate desired portion. These two possibilities are in the physically realizable filters. We know that the upper sideband filter is given by, so this is our upper sideband filter and this is going to be our lower sideband filter. Band pass filter, so for upper sideband and for lower sideband. band pass filters, minus FC minus W, FC plus W, here FC minus W 0, here minus FC plus W minus FC. So this will give either upper sideband and this will give either the lower sideband. H of upper sideband filter and this is our lower sideband filter. 0 to W and here it is 0 to minus W. We can call it as upper sideband filter. A lower sideband filter. So the block diagram is, we still have this question is in our mind, but the block diagram is, we have seen M of T using a product modulator is multiplied with the carrier signal and the resultant double sideband suppressed carrier signal is given to the sideband filter, either to the upper sideband filter or to the lower sideband filter using the band pass filter characteristics. Earlier we have seen the Hilbert transform, using the Hilbert transform. Now using the band pass filter we are going to achieve AC cos 2 pi FCT. So this is our carrier signal. Now to obtain single sideband SC, lower sideband, the filter must extend from minus FC, plus FC minus W to FC and then suddenly change over to stop band, that is it will extend to minus this FC minus W to FC and then it will go to, so this is our pass band and this is our stop band. But this sudden transition, this must be our pass band and then it enter into the stop band region without any transition band. If it goes like this, then our part of the undecided portion will also get added into the single sideband suppressed carrier. If it attenuates here itself, then the undecided our message signal, we were not able to exactly recover our modulating signal. It will leads to information loss. Therefore, what we have to do, we have to, so that is a problem not realizable. We are discussing the same topic here. Therefore, what we have to do, by using the exploiting the property of energy gap between the two frequencies, that is we have to modulate the signal, our modulating signal should have an energy gap near the zero frequency, that is we have to exploit the property of energy gap. Assume this is our message signal. We used to consider our energy signal without the energy gap, that is here energy gap is 0. At the center frequency, that is at 0, energy gap is also, we have taken it as minimum, that is 0. But here for single sideband suppressed filter, in a filtering method we are considering, since the physically realizable filter cannot be go into transition band, in this transition band, stop band region cannot start abruptly, so it needs some portion of transition period. So we are considering the energy gap between frequencies, that is in the upper sideband and lower sideband. The thumb rule for is 2 alpha by FC is greater than or is equal to 0.01. This is the thumb rule for the energy gap. So this is our F minimum energy gap and then F minus of F minimum, and this is our F max minus of F max. It should have a energy gap. So this is our energy gap period. 2 alpha represents the separation between, this alpha term represents the separation between upper sideband and lower sideband in DSP-SC signal. So if we have an energy gap in the upper sideband and lower sideband, so when we pass through this either a lower sideband filter or through a upper sideband filter, we were exactly equal recover the portion of upper sideband, we were completely recover the lower sideband, or we can completely recover the upper sideband. This is our lower sideband and this is our upper sideband. So we can completely recover our sidebands. But if we don't have an energy gap between those two sidebands, we will end up with either loss of information, or we will end up with using a more transmission bandwidth. So this should be, energy band gap should be twice the F minimum. This is our energy gap. Assume this is our local oscillator. When it is passed through the balanced modulator, this is our audio input. So practical SSB transistor will be like this. This is our crystal oscillator to produce the local carrier frequency oscillator. This is our audio input. So this is our M of T. Passing through the product modulator, we can call it as a balanced modulator or a product modulator. The resultant will be passed through a sideband filter. Yes, sideband filter. The obtained information is the S low SB or USB, either upper sideband or lower sideband. So this is our single sideband transmitter. To overcome the problem in the single sideband suppression filters, we can also use the, instead of this single stage, we can also go for the two-stage modulators. The second method we are going to see is referred as phasing method or Hartley modulator. Phasing method, or in the previous case, by using the property of energy gap, we can use the band pass filter. If we don't have an energy gap between the two signals, then we can go for the phasing method. We were not able to achieve the energy gap between two signals. X of t is our input signal. We can take it as M of t or X of t, our input signal. Then here it is, I could have included this 90-degree phase shifter. It is passed through the balanced modulator. We have upper path and lower path. So 90-degree phase shifter means it represents our Hilbert transform. Just now we have seen when we convert our time domain signal into another time domain signal using a 90-degree phase shifter, then it represents our Hilbert transform. So here we will get X cap of t, the same signal in time domain with a 90-degree phase shift. We are going to apply this signal into the balanced modulator in the lower path. So we have two balanced modulators here. Carrier signal C of t, which is AC cos to omega ct or 2 pi fct. We are applying this to the for the upper path. We are directly applying the carrying signal. In the lower path, again using the 90-degree phase shifter. Therefore, here our signal will be cos sin omega ct. Here it is AC cos omega ct. The two resultant signals, therefore the upper path and lower path all enter into the summer, plus and minus. It will be given to the linear power amplifier for amplification. That is to boost up the power level. This is our single sideband suppressed carrier. Plus sign is for lower sideband, minus sign is for upper sideband. Here we have given both the signs, so we have to use for plus sign for lower sideband filter and minus for upper sideband filter. Here the resultant signals will be half into AC x cap of t. Here we have used a minus 90° phase shifter, therefore our signal will be cos omega ct, and here our signal will be AC x of t. Directly x of t is multiplied with the balanced modulator, therefore x of t cos omega ct. So this is our input from the I channel and this is the input from the Q channel. I is the in channel and this is the quadrature channel. Upper path and lower path. Therefore, our signals via the in channel is given by m of t AC cos 2 pi fct SQ through the quadrature channel m cap of t AC sin 2 pi fct. The output is given by S of t will be summer, we have used the summer here, therefore S I of t plus for lower channel and minus for upper channel, then SQ of t will give m cap of t AC sin 2 pi fct plus m of t AC cos 2 pi fct. This is our output for the phasing method. Now we are going to see the demodulation. In the generation method, we have seen two methods. One is filtering and another one is phasing method. And now we are going to see in the demodulation coherent detection method. The coherent detection method, we know that to achieve the coherent or synchronous detection, the local oscillator used in the transmitter portion and the local oscillator used in the receiver portion must have same in phase and frequency. Therefore, this is our single sideband suppressed carrier waveform. So, this is our local oscillator cos omega ct. The resultant will be V naught of t passed through the low pass filter. And the resultant is our m dash of t, m dash of t. This is for coherent detection. We know that this local oscillator will have local oscillator. We can mention it is local oscillator will have same frequency and in phase with respect to that of the transmitter. Transmitter and receiver both should have same frequency and in phase. Therefore, we know that time domain expression for SSB of SC is given by, we take it for lower sideband AC by 2 m of t, here we have missed that AC by 2 m of t cos 2 pi fct plus AC by 2 m cap of t sin 2 pi fct. So, this is our equation number 1. It is multiplied with the local oscillator frequency signal. Therefore, the output of product modulator is given by we know that it is V naught of t. V naught of t is equal to S of t into C of t. So, this is our S of t, equation number 1. Therefore, when you substitute our S of t into C of t, therefore, AC by 2 m of t cos 2 pi fct plus m cap of t sin 2 pi fct. This is equation number 2 and multiplied with cos of 2 pi fct. Therefore, our output will be AC by 2 m of t cos into cos, therefore cos square 2 pi fct. We know that the trigonometric identity formulas, with the help of trigonometric identity formulas, we are going to substitute. Therefore AC by 2 into m cap of t sin 2 pi fct into cos 2 pi fct. We are going to replace this cos square theta with the trigonometric formula 1 plus cos 2 theta divided by 2 is equal to cos square theta, and sin A cos B will be replaced by, using the trigonometric identity, sin A plus B plus sin A minus B by 2. So with the help of the trigonometric identity formula, we are going to solve this equation. We are taking this as equation number 3. So with the help of this trigonometric identity, V naught of t is given by AC by 4 m of t 1 plus cos 2 theta plus AC by 4 m cap of t sin A plus B. Therefore 2 pi fc plus 2 pi fc, it will gives 4 pi fct plus sin of 2 pi fc minus 2 pi fc 0, sin 0 will result and will be 0. Therefore our V naught of t will be AC by 4 m of t plus AC by 4 m of t cos 2 theta will be 2 into 2 4, therefore cos 4 pi fct plus AC by 4 m cap of t sin 4 pi fct. These two are having higher frequency, only this term will be passed through the low pass filter. Therefore output of low pass filter is given by V naught of t is equal to therefore m dash of t, output of low pass filter is m dash of t, that is equal to AC by 4 into m of t. These two terms are unwanted terms, that is high frequency terms, therefore only this term will be passed through the low pass filter. Therefore the f cutoff of the low pass filter is given by omega, which is RFM. Modulating frequency should be less than the f cutoff of the low pass filter. This frequency should be lesser than 2fc minus w, again w is 2fm. This is the cutoff for the low pass filter. That is, if we have a signal or message signal m of f, which is minus w and plus w, this is RF, the resultant spectrum is this is minus 2fc and here 2fc, 0, minus fc, plus fc. So the low pass filter will have, it should be greater than 2fc minus w. Here minus 2fc plus w. Therefore our cutoff frequency should be less than that of the fc, and then should be greater than that of the fm, and then should be less than that of the 2fc minus w. This is our f cutoff frequency to entirely pass through our message signal AC by 4. So this is the, it's not fc, right, it's fm. Therefore fc should be greater than, our cutoff frequency should be greater than f modulating frequency and should be less than the 2fc minus w to avoid the overlap between these two frequency components. It will eliminate the high frequency components lying in the right and left side, only it will pass through the message signal. So this is our amplitude spectrum in frequency domain form.